Okay, so this is number 4 on the McGehee worksheet. So we have a graph that represents the net force. So net is a key word. So maybe there's friction, maybe there's not friction. It doesn't matter because we have a graph that tells us the net force. So for example, let's say it's frictionless. If this is a frictionless surface, then the net force would simply be the force, acting on the object. Well, what if there was friction? Well, then the net force would include the friction, but either way it doesn't matter because we're told what the total force is from the graph. All right, so first question, the net work done on the object after it's moved 1 meter. So we're using the graph here. So 1 meter is right here. There's the 1 meter position. Key thing, when you have a force versus displacement graph, the area under the graph is going to be the work done, right? And don't memorize it. You should be able to figure it out. Because look, when you're calculating the area here, how are you doing it? You're going base. So what's the base measured in? It's the change of position, right? From here to there, what was the change of position? 1 meter. Another name for change of position is displacement. So when you calculate the area here, you're basically going displacement multiplied by force. What's force times displacement? Work. So since this is net force, so work equals force times displacement. Since the graph is giving us the net force, this must be the net work. Does that make sense? So the answer to the first question is simply the area under this graph, which is 2 joules. Okay, second question. The change in the kinetic energy as the object moves from 0 to 3 meters. So now we're going from here, from 0 out to here. All right? So the change in kinetic energy. One equation that's really good to keep in mind, the net work done, total work done, is always equal to change of kinetic. Always, always, always. Change of kinetic equals work net. So really, the way you could solve part B, again, what are we doing? We're taking the area out to this point right here. So we're going to be calculating all this area in here. So I would break this into a rectangle and then do this triangle separately. So the rectangle here, this works out to give an area of 4. And then this triangle is 1. And then what's the work done right here? 0, because the force is 0. So the total area here is 5 joules. That's the answer. Oh, and another way you could have done this, you could have used this master equation right here. Look, you could have figured out what the change of kinetic was. So this problem does not involve any potential energies, right? No potential of gravity, no potential of spring. It's not going up a hill, so there's no potential of gravity. There's no spring, so the potentials all go away. So if you take this big master equation and rearrange it, what you'll get is the work done equals kinetic final minus kinetic initial, like that, which is the change of kinetic. Right? All right, so it's the area. Part C, the net work done as it moves from 3 to 4. So again, we're just doing area. Okay, the net work done as it moves from 3 meters to 4 meters. Oh, what do we notice here, though? From 3 meters to 4 meters, which way is the force on the object? It's negative, which means what? Is the force pointing to the right for the object, or is the force pointing to the left? To the left, because we're saying to the right is plus, to the left is minus. So this negative force means that the force points to the left. So it's working against the motion. Is this part right here, is the work done here making the object go faster or making the object go slower? Slower. Negative work is work done opposite motion. So to answer part C, you're calculating this area, which comes out as -1 joules. Negative meaning against the motion. All right, part D, the trickiest part. We're looking for the speed of the object after it's moved 4 meters from the initial position. All right, so first thing you got to calculate is the total work done. So this rectangle was positive 4 joules. This triangle was positive 1. And then this is negative 1. So everything said and done, what was the total work from 0 meters to 4 meters? The work net for the whole graph is what? Positive 4. Now, here's our master equation that we've been using. So basically what we have, the work net here, the work non-conservative, is positive 4. All the potentials cancel out like this. Do we start with the kinetic? Yeah. Why do we start with the kinetic? Because it tells us in the problem right here. When the problem begins, the object has an initial velocity of 2, right? So don't set the initial kinetic equal to 0. So you're going to take this equation, and what you're left with is kinetic initial plus the work net, which is the non-conservative work, is going to equal kinetic final, right? So this is your master equation for part D. So now what you do is you plug into that. You go, okay, so kinetic initial is 1/2 mv initial squared plus the 4 joules equals 1/2 mv final squared. The only thing missing in this equation is v final. So you solve for v final, and it comes out as 4 meters per second.